Okay, into the final subtopic of the electricity and magnetism topic, and that is electromagnetic induction. This is, well, relatively new part of the course. I know it sometimes does cause me a little bit of confusion sometimes teaching it, and sometimes I know it does cause a little bit of confusion with students, but I really made an effort with this one to try and really get it back down into some simple terms that hopefully you can understand. It is a really important topic. It is the basis of how electric motors work. It's the basis of how generators work. It's the basis of our transformers that work, that bring us all our electricity, and that are in many of the devices that we have in our own homes. It's also how basically traffic light cars detect your car at a traffic light and know to change the lights. It's how metal detectors work that look for gold and other things, lost coins on the beach or whatever else you see people out looking for with metal detectors. So yeah, incredibly important application of electricity and magnetism is electromagnetic induction. And yeah, I'm thinking as I think there's even a lot of other applications I haven't covered that you might have picked up if as you go through this. Please let me know what you think of this video. As I said, it might still need a little bit of work, but I'm trying to get my explanations a little bit clearer about this topic. I must admit it is one that I've struggled to find some really good explanations of to try and bring you guys to explain stuff. Okay, let's get into it. So firstly, we need to know what magnetic flux is. Magnetic flux is defined as the product of the magnetic field strength and the area perpendicular to the magnetic field. As we go on, I think what we mean by the area perpendicular to the magnetic field will become more obvious. It's given the symbol phi from the Greek alphabet, and the units are either Tesla from the magnetic field strength, meters squared from area, or also magnetic flux is often given its own unit, Webers, which has the symbol WB. So you basically need to be able to calculate magnetic flux, and as we go on, I think it'll become obvious what you need to do there. So just for now, remember what magnetic flux is, the product of the magnetic field strength and the area perpendicular to the magnetic field. Now, we already learnt in the last topic that a moving charge or a current, which is made up of moving charge, will create a magnetic field. So yeah, whenever we have a current carrying wire, a magnetic field will get created in the region around that current carrying wire. And we've looked at the shapes and some of the properties of those magnetic fields already. So electromagnetic induction is basically the opposite of that. And that is a changing magnetic flux induces a potential difference in a conductor. So, if you've seen me do this demo in the lab, if you get a coil of wire and you hook it up to a ammeter or a multimeter, and if you push a magnet through it, you will see you get a spike in either the current or even the potential difference. So that moving magnetic field through when a conductor moves through a magnetic field, or a magnetic field moves through a current, it will induce a potential difference. So we sort of demonstrate that. This is a bit like what we did in the lab, where we get a permanent magnet and we put it into the coil and we see that registers on the multimeter. Now, a little bit about terminology. Potential difference, also we call voltage, so voltage is the same as the potential difference. And it's also referred to as the electromotive force, or the EMF. So when you see the terms potential difference or voltage or EMF, they all mean the same thing. Don't let it confuse you too much. We just tend to talk about EMF when we are talking about electromagnetic flux. A changing magnetic flux can be caused, I've already sort of covered this, by two things: relative movement of the conductor. So in this case, if the coil is our conductor and that moves relative to the magnetic field of the permanent magnet, that will induce a current. Or if we move the magnet with respect to the coil, it's the same thing. That's why we use the word relative. That will cause a changing magnetic flux, which will then induce a potential difference. We can also, though, cause a changing magnetic flux by changing the magnitude of the magnetic field strength. So in this case, if rather than using a permanent magnet, we used an electromagnet, when we switch on and off the current, as it switches on, that creates a magnetic field, so that creates a changing magnetic flux. Or as we switch off the current, that causes a decrease in the magnetic field, so that also causes a changing magnetic flux. And the extension of that is when we use an alternating current supply. So in an alternating current supply or an AC power supply, the positive and the negative are always alternating. That means that the magnetic field, the direction of the magnetic field is always oscillating, so that therefore creates a changing magnetic flux as well. So, yeah, basically 3 ways we can create a magnetic flux. Movement of a conductor with respect to a permanent magnet, a variation of a magnetic strength by basically having an electromagnet which is constantly changing direction due to an AC power supply, and finally, well, from switching it on and off. I did them in a different order there. Now, if you haven't seen this in the lab yet, or even if you have, I strongly encourage you to go to this PhET simulation of Faraday's law and just have a play around with sort of what this looks like and just get a really good mental picture of the idea at a very simple level of electromagnetic induction. Okay, let's keep moving. Okay, let's get into the little bit more complex stuff, but hopefully not too bad. So, firstly, we can work out the magnitude of the induced EMF using Faraday's law. So this is what the first bit here is talking about. So for a straight conductor travelling through a magnetic field, so a changing magnetic flux, the EMF is equal to the changing magnetic flux divided by the change in time. And if we have a coil, then the EMF is equal to the number of loops in the coil. So N is the number of loops. I probably should have put that there. Number of loops is N times by the changing magnetic flux divided by time. So basically where we need to work out the magnitude or the size of the EMF, we just use those 2 formulas. Where we want to work out the direction, we use Lenz's law. So Lenz's law says the direction of a current created by an induced EMF is such that it imposes the change in magnetic flux, producing the EMF. So if you're like me, that statement's a little bit confusing and you've got to think about it a little bit. So let's firstly look at these diagrams here. Sorry, use my cursor. This diagram here. And if we consider we have a loop of wire and it's moving into the magnetic field, and say this is just hooked up to an ammeter so we can tell the direction of the current here. I haven't drawn that in. But that loop is moving into the magnetic field. And then, so it's an experience an increase in magnetic flux. As it moves in, it's going from not in a magnetic field, moves into it. There's an increasing magnetic flux. Now at the moment, the magnetic field is into the page. The crosses mean into the page. So that means that the EMF will act in a way to counteract that change. So that means it's going to want the magnetic flux that's created by this loop is going to want to be coming out of the page, because that's the opposite of going into the page. As it moves in, is experiencing into the page, that's the direction of the change it wants to oppose. So we can think of it like the magnetic field wants to come out. And here we can use the right hand rule. And the right hand rule, you basically want your thumb, oops, I didn't mean to draw that, just meant to laser that. You want your thumb to point in the direction of the change in the magnetic flux. So because it's increasing as it goes in, it's going to decrease it. So that means we want basically that magnetic field that it's creating to be out of the page, so the thumb would here point out of the page, and the fingers would show the direction of the current. So if you've got your thumb pointing out of the screen, you can see with your right hand that your fingers curl around in an anti-clockwise direction. Go back to a pen. An anti-clockwise direction. So that would be the direction of the current in that loop here. Now if we go over to the case in red, here we are leaving the field, so we get a decreasing magnetic flux. So decreasing magnetic flux. That means that the current is going to flow in a way that would effectively increase the magnetic flux. So the magnetic field is into the page, so it's going to want to create a magnetic field that also goes into the page because it's decreasing. So if you point your thumb down into your screen or down into your page, if you've got the notes there, and you look right hand at the curl of your fingers, you'll see that your fingers are curling in a clockwise direction. So that's the direction as given by Lenz's law. Just for completeness, I'll just add increasing magnetic flux there. Now, so that's from the movement of a conductor through a magnetic field. Let's have a look here where this case with a changing field. So let's say we've got a field here indicated by the yellow crosses that's going into the page. That magnetic field is increasing. Say that's an electromagnet, it's just been turned on, so the magnetic field is increasing. The current will flow in that wire that creates a magnetic field in the opposite direction. It will try and decrease the field as it's increasing. For those of you who do chemistry, this is a bit like Le Chatelier's principle. It's opposing a system at equilibrium. So in this case, the thumb would come out of the page because it's increasing, so it's trying to oppose that, or out of your screen. With your right hand, you look at your fingers, they curl now in an anti-clockwise direction, so the current would flow that direction there through that wire. We're going to look at these a little bit more too in detail. We've got a couple of examples down below where we've got a permanent magnet and it's moving through a coil of wire. So as that moves through here, the coil, the current that flows through this coil, or at least through this cylinder as it looks in the diagram, it did look like a coil in a bigger diagram when it was blown up, but it doesn't matter. It's going to want to create a magnetic field in the opposite direction. So the magnetic field that it's going to want to create is going to point in the opposite direction as to the magnetic field from the permanent lines. Again, if we use our right hand rule, that means that the thumb is going to want to point to the left. So those arrows point to the right. The thumb's going to want to point to the left. Where do our fingers curl? Our fingers are curling up. If our thumb is pointing to the left with our right hand, so yeah, right hand, thumb pointing to the left, the fingers curl up, and you can see that would be the direction of the current. If we were going to pull this out, then as we pull it out, it's going to basically cause a decrease in the magnetic flux. So it's going to try and act to increase it as we pull it away. It's going to cause a decrease in the magnetic field strength in this region around the coil. So as we pull it out, it's going to want to try and increase that. So if it's increasing that, we want the magnetic field lines to point to the right. So if our thumb points to the right, we can see at the thumb pointing to the right, the fingers curl, if you like, at the back here of the coil, they're going to be going upwards, which will mean as you bring your finger right around, hope you don't get a sore wrist, you'll see at the front of that coil, the current will be flowing downwards. So that is Lenz's law and how we work out the direction of the current that is induced due to the induced EMF due to the change in magnetic flux. So we also need to consider how this is consistent with the conservation of energy. So how Lenz's law is consistent with the conservation of energy. So if you consider the diagrams A and B here, if the change in magnetic flux induced an increase in magnetic field, this would cause the poles to cause the current to flow in the opposite direction and the poles of the coil to be reversed. So as we move this into here, if the result was that we tried to get an increase in magnetic flux, that would mean instead of the magnetic field lines going this way and the current therefore going that way, the current would go the opposite way. The magnetic field lines would point in the same direction. This would become the south pole, this would become the north pole, and the magnet would actually be accelerated towards the coil. The permanent magnet would then be accelerated into the coil, that's what I just said, causing an increase or a further increase in magnetic flux and therefore an increase in EMF and induced current. So the faster it went, the more and more current you would get here. This would cause a further increase in magnetic field and the permanent magnet to accelerate further and further without the input of energy. So basically we would put this here, it would accelerate, the current would cause it to, we'd start pushing this in, the current would cause this to become, the magnetic field lines to point in the same direction. So the north pole here would then be attracted further because the north pole moves in the direction of the magnetic field lines. It would basically experience a force, so it would be accelerated more. The more it got accelerated, the greater the EMF would be, therefore the greater the current would be. We'd have this basically never-ending cycle of increasing the speed of the magnet without actually putting any energy in. This would violate the law of conservation of energy, but it would be a great way to make a perpetual motion machine, or even better, a perpetual acceleration machine, to accelerate any magnetic material towards the speed of light. Now, obviously, this doesn't happen. If it did happen, it would not obey the conservation of energy. You cannot get more energy out of a system than you put in. And if the magnetic flux that was induced was in the same direction as the original, or as the change in magnetic flux, that's what would occur. So that's why it's not consistent with, Lenz's law would not be consistent with conservation of energy. That's why the current always flows in a direction that creates a magnetic field that opposes the change in magnetic flux. That bit is a little bit confusing. It is probably one of the harder explanation questions I think you could get in this course, maybe along with some of those conservation and momentum ones that we did at the end of the last topic. If you're not clear about that, read over this a couple of times, look at the diagrams, see if you can make sense of that. If you can't make sense of that, come and talk to me and we can talk about it some more. As I said, it is a little bit of a tricky one to get your head around, but once you get your head around it, it seems pretty simple. Yeah, quickly when I look at it, I go, well, as this moves in, if the current went downwards, then we'd use the original right hand curl rule, thumb down. That would cause an increase in the magnetic field. The magnetic field is the direction of force experienced by a north pole, so this north pole would get accelerated further. As it got accelerated further, that would increase the amount of current. If it increased the amount of current, that would increase the magnetic field strength inside the coil, and it would just accelerate and accelerate and accelerate without having to input any energy. Therefore, it doesn't meet conservation of energy. Hopefully you've stuck with me that. Please let me know. If you followed that explanation, please let me know so I know. If you didn't follow, let me know, because I might go back, redo this video and try and make it a little bit better. Let's move on. Okay, So now we need to talk about eddy currents, and we need to use Lenz's law to explain the production of eddy currents. So whenever we have a conductor moving through a magnetic field, we will create these eddy currents. These eddy currents have important applications in basically brakes, particularly on things like high-speed trains. They also are used often in power tools where we have metal discs that are spinning really, really quickly. So we basically have a conductor that's spinning very quickly. If we make that move through a magnetic field, it will create these eddy currents, and they basically have the effect of causing a force that acts in the opposite direction to the rotation, so they cause it to quite a large braking force and cause it to brake very quickly, and also cause that to happen without the need for friction. These are also used in things like induction heating elements and that sort of thing, which we won't go into in detail here, but you may come across referenced in some places. So let's see what happens. If we have got here this metal conductor, or a conductor, assume it's a metal, and it's going to move into this magnetic field. So V is the velocity vector, so that says the direction that it's moving. What's going to happen here? Well, as the conductor enters the magnetic field B, shown here, it experiences an increase in magnetic flux. So it's entering magnetic field, the magnetic strength is increasing, there's an increase in magnetic flux. The eddy current is created that opposes the change in the magnetic flux. So in this case, as the magnetic field B is into the page, that's what the crosses mean, the eddy current creates a magnetic field that will be out of the page. So the eddy current, we're using our right hand rule now, thumb's coming out of the page or out of your screen. Right hand, that's the direction that the magnetic field is created that opposes the increase in the flux because the magnetic field was into the page and it was entering, so it was increasing. And we can see from the right hand rule that the thumb, magnetic field out of the page, and the fingers curl counterclockwise here, which shows you the direction of the eddy current in the conductor. So let's also quickly look at what happens as it leaves the magnetic field. In this case now, we'll just do this in a bit more shorthand way. In this case, the magnetic flux will be decreasing. So a down arrow is a shorthand for decreasing. So as the magnetic flux is decreasing, then the eddy current will try to create a eddy current will create a increasing magnetic flux. So in this case here, as the magnetic field is going into the page, the eddy current is going to try and create, maybe don't even need a dot point there, let's just do that as a i.e. it's going to try and create a magnetic field that is also going into the page, and then we can use the right hand rule. So now our thumb's pointing straight down into our screen or into our page. We're using our right hand. If we look at which way our fingers are curling, we can see the eddy current will move clockwise. So that is how we use Lenz's law to explain the production of eddy currents. Let's move on to the final slide. So we can probably think of eddy currents as the first application of electromagnetic induction. And now we're going to look at a couple of others. We need to look at generators Just very, very briefly, we just basically need to explain how generators can be used to produce electric current. We're not going to do any detail here. And then we're going to look at transformers, and we'll look a little bit more in detail at transformers. So firstly, we know that wherever we have a conductor moving through a magnetic field, that will induce a current. It will induce an electromotive force or a voltage, and therefore a current in that wire. So if we basically have a loop of wire here and a permanent magnet, as this spins through, that is going to, or in this case it's going to spin this way, that is going to create a current that flows through that wire for what we just talked about there with Faraday's and Lenz's law. As the current moves through, it basically experiences a change in magnetic flux that basically induces an EMF. An EMF is a voltage. A voltage induces the movement of charge, which is a current. So we can use that to basically generate a voltage and a current. Now, if you're interested in this stuff, and I know some of it's in the textbook, you can go in and look at how AC generators work and DC generators, and there is lots of interesting and cool stuff related to this stuff, but you don't need to know that level of detail for this course. You just need to know that basic idea of how you can use Faraday's law, and I guess Lenz's law as well, to generate a electric current by moving a coil of wire through a magnetic field. The other application that we need to look at, and we do need to know a little bit more detail about this one, is how transformers work. So transformers are used to convert voltages. They are really, really important. For example, our electricity that gets sent from power stations is sent at very, very high voltages. That helps minimise losses due to the resistance of the lines and makes it a more efficient way to transport the electricity. But it's not a good idea to have really, really high voltages coming into our homes, because that's really, really dangerous. So we use transformers to turn it down back to 240 volts, for example, when it goes into our house. Also, our microwave ovens, even a lot of computer power supplies, battery chargers, all sorts of things like that also have these transformers in them, where we need to change the voltage from one voltage to either a higher or a lower voltage. And basically what a transformer consists of is this solid iron core, and then we have our primary coil here. This is our primary coil. NP is the number of loops in our primary coil. IP is the current through our primary coil. VP is the voltage of our primary coil. Now, important, we always have to do these with AC voltage, because what we need to create to make these work is a changing magnetic flux. If we have a DC, then we have a constant current, so we don't have a changing magnetic field, so we don't have a changing magnetic flux. So this basically wouldn't work. So what happens is this current flowing through this coil, which is constantly changing because it's AC, will induce basically a current to flow, or it'll induce a magnetic flux or a magnetic field in this iron core that will cause a current to flow through that, or that will, sorry, not a current, that will induce a changing magnetic flux in this iron core. That's probably the best way to say that, so let me say that again. Changing current here induces a changing magnetic flux within this iron core. And this side, that changing magnetic flux is moving through a second coil. That second coil will then basically, there will be an EMF and a current, so a voltage and a current will be induced into this secondary coil, and then we can look at the secondary current, the current in the secondary coil, the voltage in the secondary coil, This just signifies some load that might be on the transformer, like your microwave oven or your house in the case of a transformer in an electricity grid. Now, the important thing that you need to know in terms of the mathematics is that the relationship between the voltage in the primary coil and the voltage in the secondary coil is, well, the voltage in the primary coil divided by the voltage in the secondary coil is equal to the number of turns in the primary coil divided by the number of turns in the secondary coil. So we can get two types of transformers. We can get a step-up transformer. Here, the number of coils in the secondary coil, so the number of coils in the secondary coil is greater than the number of coils in the primary coil. Therefore, the voltage in the secondary coil will be greater than the voltage in the primary coil. It's maybe easy to think about with this formula. NS is bigger than MP, so VS will equal NS over MP times VP. So if this is bigger than 1, then the voltage in the secondary coil will be greater than the voltage in the primary coil. But the trade-off is that the current in the secondary coil will be less than the current in the primary coil. You could look at Ohm's law from year 11 and think about that. But we're not so interested in what's happening with the current mathematically. We only need to worry about what's happening with the voltage and the number of coils. In a step-down transformer, which is maybe what's more common in an electricity grid, the number of coils in the secondary coil is less than the number in the primary coil. Therefore, the voltage in the secondary coil is less than the voltage in the primary coil, but the current in the secondary coil will be greater than the current in the primary coil. So, I think the questions on that are usually fairly straightforward. I did think about putting an exam question in here and going through it, but generally it's just basically reading the question, identifying what's the primary coil, what's the secondary coil, how many turns in each coil, and therefore, well, how much voltage is in the primary coil or how much voltage is required in the secondary coil, and then working out what must have been the voltage in the primary coil, or given the voltage in the primary coil, work out the voltage in the secondary coil. If you have any troubles with any of those questions, please sing out and I can spend a little bit of time going through them, but generally they are not all that tricky. Okay, thank you very much.